In part 2 of the Unit 3 notes, we are going to be covering the discovery of subatomic particles. In our last video, we were discussing John Dalton's atomic theory. In that theory, he stated that atoms cannot be subdivided, created, or destroyed. Based on this, the Dalton model of the atom is essentially a solid sphere. So in the early 1800s, scientists believed that the atom could not be broken down any further, and they did not have any idea about subatomic particles at that point. In the late 1890s, English physicist J.J. Thomson began a series of experiments on cathode rays. Cathode rays are a stream of radiation passing through a tube between the cathode and anode when an electrical current is applied. Here you can see a diagram of a cathode ray tube. So when the current is applied, you see this green laser beam going from one side of the tube to the other. So that is our cathode ray. During this experiment, J.J. Thomson used the negative or south end of a magnet, and he brought it in towards the cathode ray, and he saw that the cathode ray was repelled by this, just like what you see in this picture here. Now, when he flips it around and has the north or positive end, the cathode ray is attracted to it. Now, based on what we know about charges, so opposites are going to attract and like charges are going to repel, that tells us something about the cathode ray itself. It tells us that those cathode rays are negative. Now, Thomson also tried this using other types of cathode material, but he found that the same negatively charged particles with identical properties were emitted in each case. He concluded that this particle was a fundamental part of all atoms. For your first checkpoint question, based on your current knowledge, which subatomic particle do you believe J.J. Thomson discovered? Now, up until this point, we learned that cathode rays are negative. And you most likely know from previous science classes that electrons are the negative subatomic particle within the atom. So J.J. Thomson was responsible for the discovery of the first subatomic particle, which was the electron. In the early 1910s, Robert Millikan was able to determine the charge of an electron using the oil drop experiment. He later identified the charge as 1.602 times 10 to the negative 19th coulombs. This was later equated to a single negative charge. Essentially what you have here are oil droplets which are going to be suspended between two charged plates, and they were observing those with this microscope. Using the charge of the electron, Millikan was able to determine the mass. The mass of an electron is 9.1 times 10 to the negative 28th grams, an incredibly small number. And this was about 1/2000th the mass of a hydrogen atom. Now the significance of that is that hydrogen is the smallest element. So he was finding something that was 1/2000th the size of the smallest thing that had ever been discovered before. At this point in our atomic theory timeline, which is early 1900s, we know that atoms are electrically neutral. We also know that the mass of the atom is very large compared to the mass of the electron. What does that tell you about the rest of the atom? Draw a picture in your notebook of what you think the atom might look like based on this information. So at this point, you should pause your video, fill in your picture within your notebook, and then you can continue. J.J. Thomson proposed the Plum pudding model. So this was his picture based on what he knew about the atom, electrons, and the overall neutral charge. So in this model, negative electrons are spread evenly through positive charge in the atom. This results in a neutral atom overall. There is no nucleus at this point. So I know a lot of you are probably already familiar with other subatomic particles and the nucleus, but at this point, only the electrons had been found. So in J.J. Thomson's model, the entire atom is this big, massive positive charge spread throughout the entire thing. And we have these very small negative electrons that are spread evenly throughout it, like what you would find in plum pudding, or what might be a little bit easier for you to visualize, a chocolate chip cookie. All right, next up, in 1911, Ernest Rutherford conducted an experiment to see if positively charged alpha particles would be deflected as they passed through a thin gold foil. This experiment is known as the gold foil experiment. So this foil is essentially the same as what you would consider like aluminum foil. It's just made out of gold, so similar thickness. And in our experiment here, you can see that you have your alpha particles being shot from this block. It's hitting the gold foil and then passing through. Now, working off of the plum pudding model, Rutherford believed that alpha particles would pass through with only slight deflection because the positive charge was thought to be evenly distributed. And you can see that in this picture over here. So if this is the plum pudding model, the alpha particles should have passed straight through without really having any deflections because everything was evenly charged and evenly distributed. However, in reality, a few alpha particles were deflected at large angles, and 1 out of every 8,000 alpha particles were deflected back to the source. So that's what you see down here. So some of the alpha particles are going through without any problem, just as he had originally predicted. But a few of them are bouncing off to the side, or they're actually getting bounced back to the source. All right, for your next checkpoint question. The gold foil experiment proved that the plum pudding model was not accurate, since positive particles were deflected. How could you redraw the model in order to explain this anomaly? Draw a new model of the atom in the notebook based on this. So at this point, you should pause your video for your drawing and then continue. The gold foil experiment proved that there is a powerful and positive force in an extremely small amount of space since so few particles were affected. This densely packed bundle of positively charged particles is known as the nucleus. The positive part of the nucleus, which is responsible for the deflections, are called protons. Electrons exist somewhere outside the nucleus. This is now known as the nuclear or Rutherford model. So whereas in the J.J. Thomson plum pudding model, the positive charge was spread evenly throughout the entire atom, we now know that all of that positive charge is in a very tiny space in the very center of the atom, known as the nucleus. Now there's a quote that Ernest Rutherford has after this experiment, which I find interesting. So he said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you." So this was definitely not something that they believed would be possible. In 1932, James Chadwick found that the mass of the protons in an atom was less than the total mass. This, combined with the fact that electrons have essentially no mass, proved that there must be a third neutral subatomic particle. A German physicist, Werner Heisenberg, proved that this neutral particle could not be a proton and electron pairing, and was in fact a new, unique particle, now known as a neutron. Neutrons are important because they act as a buffer particle inside of the nucleus, so that the positive protons do not repel each other. Here we have a chart which summarizes what we've learned so far about each of these subatomic particles. So for symbols, you will often see these particles abbreviated as E-, P+, and N0. The charge of the proton and electron are equal and opposite. So a -1 versus a +1. And of course, since neutrons are neutral, they are a 0. Now for the mass, the proton and neutron mass are approximately the same. So we often estimate them as exactly the same, being 1. In reality, if you went further out with more places after the decimal, you can actually say that there's a slight difference there. But for our purposes, we are going to estimate that protons and neutrons are about the same mass, and electrons have no mass. Now this part is important. Electrons are considered matter. So even though we're going to estimate that they have no mass in terms of the math, they do actually have mass. It's just so tiny that it has no impact on the calculations that we do. So we kind of ignore it. Now, one last thing here about all these subatomic particles. If you wanted to try to visualize this, the scale of the atom and what exactly is happening. If the nucleus, which contains the protons and neutrons, were the size of a marble, then the entire atom would be the same as a football field. So imagine this marble at the very center of Beaver Stadium here. You would have to go all the way out to the very edge before you started to get to the electrons. So most of the atom is empty space. That concludes part 2 of our Unit 3 notes. When we come back for part 3, we will cover counting protons, neutrons, and electrons for atoms.